Candy cornium. Candy cornium. How appropriate, Halloween bowl. All right, and then, does anybody have a peanut allergy I should know about? Okay, this is M&M Peanutium. This is how you liven up a party at home. If you're having a Halloween party at home, play Candium. And make sure those are the radioactive ones. Alan's here saying, why did I come to school today? This is a mix of wild berry and tropical, but they're still all Skittles. Okay. We're gonna taste the rainbow. No, you're not gonna taste the rainbow. No spit. All right, so there we go. And I'm going to why we're taking two, one is going to be your clean cup that you're going to measure your mass in. The other will be what you count, or you're going to count them and then you're going to pour them into here, come up to the balance, put your clean cup in there and get the weight. All right, so let's do this. Go ahead and get your notebook paper out unless you have the form already set up. And what I'm going to do, excuse me, camera. I gotta go get close. Okay, can you see that at home? See that? We have bright pink. That just wants to keep flipping over. Well, those stretch nice though. They stretch better than the ones we buy. I should keep that brand name. Wow. Much better than ones we get. Okay, so much for making fun of the state. I wonder if I did this. Stay. All right, so here we go. Now, I should have enough for everybody to get a sample, but you may not want to, you want to do about half, like that, okay? And we'll see how this goes, and if this works, we might have to combine a few people's sample. But come on up, let's just start with Alan. Alan, you come on up and you grab one, and then it's right. Now, I realize candy cornium tends to break up a little bit. That's okay, we're just gonna count it as if it were a single isotope. And so now that we've done that, next thing we wanna do is carefully, don't let them fall on the floor. Fill them out, and let's sort. Just be careful with them. The candy cornium does not roll. The M&Ms will, so be careful. You could use the pencil tray. It'll work. Let's just use that since it's got a little. I'm gonna not include the little broken pieces. Skittles. This is like half one. Quite a bit in that cup. I've done this before with different M&Ms. I've never done it with Skittles and candy corn before. I kind of like it better this way. Like it's more of a variety. Now, when you are done, go ahead and you might want to count your pieces, because on your, up there, okay, so, because you're going to have to write the number of pieces in anyway, so go ahead and count your pieces. And you may want to choose a set to start with. I guess Skittles is first. Oh. Sorry, Sparky wanted to play. We're going to say these little broken pieces of candy cornium are in the process of going through fission. They're splitting apart. Even better for our story that they're radioactive. All right, so as you count them, make sure you write your numbers down. And then what we'll do is we'll choose one group. I guess we're going to go with Skittles first and put them in one of our cups. So I have in mine 19 Skittles. Now this is what we're going to do. I'm going to turn the balance on. That's helpful. Okay. And what you want to do is you're going to take your empty cup and we're going to put the empty cup on the balance. We're going to tear out the weight. Now when I say tear, that's T-A-R-E, not tear as in tear a piece of paper. We're going to remove the weight of the cup. And we're making an assumption. This is okay. In science, it's okay to make an assumption if it's valid. And since these cups were all made and processed probably at the same time, we're going to assume that they all weigh within an insignificant difference. So we're going to go ahead and I'm going to tear that weight out, and then I'm going to pour my Skittles in there. And this sample is 20.49 grams. So right here, total isotope mass, 20.49 grams. Now this is my data, people at home. This is my data. They all have their own data. And so what they're going to do is just repeat what I did. They're going to come up. Now make sure you re-zero the scale before you leave. Put your empty cup on there. Hit the 0 button once. Pour your candy in there. And then go back to your seat. Get ready for the next round. Okay? Same order as before. Alan, come on up first. totals. This is the total mass of my sample. This is the total number of pieces that I had. And what I want to do is get the average isotope mass per one piece. It is much more accurate this way than trying to weigh an individual candy piece. Because as you know, the candy pieces vary, especially the peanut M&Ms, because sometimes you get twins in there. So this is how scientists would do this. They would take a large sample and they would determine the mass per single particle. So that's what we're going to do. Except if you have to learn how to use a calculator. And remember significant figures. We're going to go to 3 significant figures. All right, very good. By the way, when you have integers, just so you know, I always got confused on this when I was learning significant figures. Integers don't have significant figures. They're just integers, okay? So when you're dividing, you're not saying these are 2 significant figures, so everything has to go to 2. These were all to 4. And I could have gone to 4 on these as well. I just prefer to go to 3 because most science we do 3. But if you wanted to, you could take this to 4 very easily. I just don't believe that my balance really goes past the 100th place. That's my primary reason for that. All right, so we're going to do this average right here, 6 grams per piece, and we're just kind of going to put a circle around it. And this is not a weighted average, so let's make a note on here. This average is not weighted. This is assuming that all pieces weighed the same. That's how you would normally take an average. If you were trying to figure out the average of women in the class, you'd add up 1, 2, divide by 2, there's your average. All right, so if we wanted to take the average of men and women in the class, the average would swing closer to the men because there's one more man in the room than there are women. So that's what we mean by an average weight. Okay, now percent abundance is, we're going to do this. This is going to be the number of pieces, 19 pieces, out of 67. So you have a big box of candy, and it holds 67 pieces of it in it. And of that, 19 of those pieces were our Skittles. So the percentage is going to be part, so 19, then divided by the whole, which was 67, equals, and then that number you're going to multiply by 100, and that'll give us percentage. Okay. So let's go ahead and do that. Change colors here. So 19 divided by 67. Now you're doing that for your day, by the way. I'll do my example up here. So this was 28%. And we call it 28.3. Keep it to 3 significant figures. this would be 100%. 67 out of 67 would be 100%. And this should add up to 100%, so just let's double check it. 28.3 plus 41.8 plus 29.9. Yeah, I get exactly 100%. So that's your check. When you add your percentages up, they should all equal 100. All right, good job. Is everyone following okay? If you have any questions, just raise your hand. Now, what we mean by relative abundance is we're going to take the fraction. We're going to take it down to its decimal. And so the fraction of 100 is going to be 1. 1.0. The fraction 29.9% is 0.299. The fraction of 41.8 would be 0.418. And this fraction would be 0.283. And again, they should all equal 1. It says mine added up to 100 is going to add up to 1. So what this is saying is which one of these is in the largest abundance in my sample? Is it the Skittles, the peanut M&Ms, or the candy corn? Peanut M&Ms. Now your samples are going to vary. A couple of you didn't have as many peanut M&Ms. So in your case, your relative abundance may be higher in the Skittles sample. Okay? That's okay. That's all right. It was a mixture. So how I get relative mass? The relative mass is going to be the mass of the isotope times its percent abundance, and then we're going to add them up. So if I take 20.49 grams, I think this is right. Total mass, or is it this? 1 second. Let me just double check. I don't want to get us off on a stray. Average atomic mass of candium. Relative mass plus relative mass plus relative mass. Relative abundance of isotope times the average mass of the isotope. Okay, so we do want the smaller number. Glad I checked that. So we're going to use this one right here. So 1.08 grams times 0.283 Okay, so that's going to be 0.306 grams. And then just keep on going here. So 2.58 times 0.418 is 1.08 grams. And then 1.58 times 0.299 equals 0.472. I'm going to double check my work on this one. Okay, so then we're going to add those up. So 0.306 plus 1.08 plus 0.472. All right. So my average isotope weight is coming out to be almost like, well, it did, came out to be identical to my non-weighted average. Can you think of a reason why in my sample they came out the same? Why do you think that happened? was the lion's share again? Was the peanut M&Ms, right? So my average is going to be closest to the average of the peanut M&Ms. See how far away though it is from 1.58 and 1.08. It's being drug up to it. And the fallacy of this simulation is that most candy manufacturers account for this when they're making candy. They sell by mass. And your heavier candies, you have fewer in the bag than the other. So in a way, they have already pre-weighted the average. But the only reason why this is coming out this way, assuming that this was all the pieces added the same, in this particular case, look at my percent of half of it was peanut M&Ms. And so it was dragging everything up. Now, if your sample actually had more Skittles in it, which way should it gotten drugged? If you only had a few peanut M&Ms, but maybe the whole thing was weighted towards Skittles, your average atomic mass should be drugged in what direction? Yeah, it should come down, right? It should come toward the Skittles, shouldn't it? Yeah. So that's okay. If they come close to your average, normally these two don't equal, because this is assuming they're all the same. The candy manufacturers are sneaky, and they're going to make sure that they get as much money out of that bag as they can. And so they will pre-weight it based on the actual average mass of that candy. So that's what makes this demonstration a little bit more difficult. But the process we went through is exactly what scientists go through with isotopes. If you take a look, well, I'm sorry, where I lost my periodic table. Look at chlorine for a minute. Its average is 35.5 grams for every 1 mole. That means there is an isotope above it and an isotope below it that are about equal 50-50. And in the case of hydrogen over there, it is so close to being just protium because the majority of hydrogen is H1. So that means the other two, which happen to be very radioactive, are much, much smaller percentage-wise. So you got like 98% of hydrogen is going to be in the form of H1. So it's definitely going to be 1 when you do the average. All right? And that's it. That's candium. That's how you calculate a relative abundance. Now, we're going to review all of this when we come back after fall break, so we can have our unit test. But now you have data and you have something in your book. What I would like you to do is in Canvas, find Canvas here, where'd Canvas go? You should have the submit button up here. What I would like you to do is fill that chart out and submit it to me before Monday or Tuesday, and you get 50 free points, because that's exactly what it was, 50 free points. Now, those of you at home, you're going to do the same thing with my numbers, or if you got a kitchen scale and you've got a bag of candy, try it at home. Do the exact same thing at home. You do have to have a scale of some sort, though.